Confirm. Okay, good afternoon everyone. This is 8th interactive session of NPTEL course Experimental Physics 2. The course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am Renalini, PMRF Research Scholar from School of Physics, University of Hyderabad. As you all know, these sessions happen every Saturday 3 to 5 pm, and this is our 8th session where usually we discuss some important derivations or concepts related to the lecture videos that are uploaded and discussed every week. And mainly we'll focus on some numericals so that you guys will be able to solve your assignments for this week. Okay, so let's have a recap of last week's things that we had discussed. So last week we had started with discussing about what interference phenomena is and what are the conditions important for it, like how we need for interference to happen. We need coherent sources. That means they should have same frequencies, same wavelength, and they should have a constant phase difference throughout. Apart from this, we also had discussed that how amplitude, although it's not required that the amplitude should be same, but if the amplitudes of the two wave which are going to interfere, if their amplitudes are closer, then the contrast of the fringes that we get is better, which is a good thing while we are carrying out any experiment. Okay. Then we had seen these are the fringes. So when we take a monochromatic light, we get these bright dark fringes. We had also derived the conditions for it, and we had seen that when we take a white light source for interfering, doing interference related experiment, then we get these. It's splitting into various components. So this is something we get when we use a white light source, and this is something we get when we take monochromatic light source. And then we had seen that we how we had discussed actually various things, how we can generate coherent source, because if we start with two independent sources of light, then it's difficult to ensure that their frequency wavelength are exactly same. That's why what usually we do is we take one source of light, and then from that one source itself we try to generate two sources. In this way we are able to keep the frequency same. As you know, frequency is the property of the source of the light or the wave of this electromagnetic wave. So here Young's double slit experiment talks about the same thing. We have one hole like this, and through this when we take one light coming, and then after this again if we put a screen or barrier with two holes, then through these two holes we'll get two sources of light or wave. So, and when we generate two sources of light in this way, they will be coherent. And then we had derived the condition for getting dark and bright fringes. We'll get something like this. And we had seen what is the relation between the distance between screen and the source of light, distance between these two sources of light, how much apart they are. And then we had derived what will be the how we can calculate the fringe width, which is same for the bright and dark fringes. After that, there were various other sources we had discussed, like Fresnel's biprism, Lloyd mirror, Fresnel's double mirror, Lloyd's mirror, and yeah. So these were the various methods again to where we are starting with single source, and then for interference we need more than one source. So we are starting in all these were different methods in which we are starting with one source, and then we are able to get another source. Here, like from this mirror, one will be reflected, one will be direct, and thus they'll interfere to give us interference, because the reflected one will have some path difference. So these were the different techniques through which we can get interference pattern as we desire. Then last week also there was this little bit discussion on how we can have something like thin film, optically different medium of different refractive index than in which the setup is, to introduce some path difference again to get a interference pattern. So there are the one that was discussed for fringes of equal inclination. So here till now we were discussing about getting fringes, that is and dark and bright kind of pattern in a linear fashion. But these lights, if they are falling on our system at equal inclination throughout the surface, then we'll get, instead of getting or linearly ordered bright and dark fringe, we'll get something like rings. Here, yeah, so if we see here, this is the source S, and we have kept a, say, glass plate which has some refractive index mu, and thickness of it is d. Here on our screen we'll be getting, so this light coming from source, it will, one part of it will reflect from this air and this glass plate interface. It will reflect and come to the screen. The other part, some of it will go inside the glass plate and then reflect from this other interface. So what happens is, we had discussed last time that when a light wave reflects from optically denser medium back into a rarer medium, this reflection from a denser medium introduces path difference in it, like phase difference of pi, which means path difference of lambda by 2. Because of this, these two reflecting lights coming from the same source now have path difference in them, and that's why on the screen they'll interfere to give us dark and bright fringes. So path difference, as you can see, this SA path is common path, both the light will be traveling, and this C to P and this D to P is also same. The extra path that the another light is traveling is AB and BC minus AD. So the path difference, if we denote it by delta, then the extra path is this AB plus BC minus AD. Here AB plus BC we have multiplied with mu because the refractive index is different here. The other distances that the light is traveling is in the air medium, whereas this AB plus BC distance that is traveling is inside different refractive index medium. That's why we are multiplying it to get the correction in the value. Now A, B and BC are equal distances, and they will be given by, if you see this angle of incidence, okay, let me first, where is the pointer, wait, so this is the normal to this interface, and this incident light is at an angle theta. Then from vertically opposite angle also we know that this angle will be theta and this angle will be theta. Now in this right angle triangle AB, and if we call it O, I mean this triangle that is right angled, here we can see that AB BC will be equal to, if we take cos theta of this, cos theta is, where should I write? Okay, so let me just try something else. What is wrong here? differentiable. Okay, I'll put this here. Yeah, so we were discussing about this. So here in this right angle triangle, if we see cos theta, this, okay. So in this triangle A, B, and some point O, say we see that cos theta will be base by hypotenuse. That means this base and the hypotenuse is AB. So base is D upon AB. D upon AB. That means AB will be B over cos theta. So this is what is here, and since AB and BC are equal, so we'll get D over cos theta. Now AD, which is this distance, that is AC sine theta, its projection, which will give 2AB sine square theta. So delta finally, which is this AB plus BC multiplied by mu minus AD. So this AB and which is also equal to BC, the values we have found out in terms of D over cos theta, and we have to subtract AD from it. So when we'll substitute values, when we'll substitute the values of AB and BC here, we'll get something like this, and then we take out common. Ultimately, the path difference delta we are getting 2 times thickness of our film times cos theta, and where theta is the angle of incidence and mu is the refractive index of this glass film or thin film or whatever this medium is. So here we see that the path difference that we will be getting, which is very important to know how the interference will be finally. It depends on refractive index of this material, the thickness of it, and the incidence angle of the light. So this we will see how we can change these things to vary what will be the center fringe in various experiments. We'll be discussing Michelson interferometer experiment and Newton's ring experiment for this purpose. Also here there is condition for dark fringe and So the condition for dark fringe becomes 2 mu d cos theta is equal to m lambda. Usually this you must have seen for condition for bright fringe, but here since path difference of pi phase extra pi is getting introduced, so path difference will be lambda by 2, and then the condition will become like this. What we want to say is this path difference. Okay, we'll see in some other experiment. So the first experiment, oh, this also we had, this was last time we had discussed. Okay, so this week, yeah, so as we were discussing this, that we'll get path difference of 2 mu d cos theta. Now the condition for dark fringe here, usually we know condition for dark fringe we get that path difference, which we get something like, if not mu, if the it's the same medium, that then we get 2d cos theta, and we know that if theta is 0, then cos will get its maximum value, which is plus 1. It means the path difference will be there and we'll get dark bright fringe. So this used to be the condition, but here since there is extra lambda by 2, that's why the conditions become opposite. This we used to see earlier. Here 2 mu d cos theta will be equal to m or n lambda for dark fringe, and the path difference will be equal to m plus half times lambda for bright fringe. This is happening why? Because the path difference here has extra lambda by 2 difference. So for a dark fringe, why we are getting like this? Because the path difference will have this extra lambda by 2. The path difference that we geometrically see here, that is fine, but because this one ray, one part of it is reflecting from this interface, one part is reflecting from this interface, and when it reflects from optically denser medium, it gets a pi phase difference. Now we know that phase is given by 2 pi over lambda times path difference. Okay, now if I'm saying it will get extra pi phase, then what will it be? So this is the phase, extra phase difference. That means what will be the path difference? Path difference will be pi lambda by 2, that I'm telling. It will have a extra lambda by 2 path difference. So for dark fringe, this extra path difference will come. So if this is the condition I'm choosing here, then it will become, you will see, it will become m plus half multiplied by lambda by 2. So which was earlier the condition for dark fringe, now becomes the condition for bright fringe. So this was the reason. Okay, and yeah, so the first experiment we'll discuss now is Newton's ring experiment. So in this experiment we want to study the formation of Newton's rings. So as I was telling, if we have arrangement in linear fashion, dark bright, we call it fringes. When we have this happens when the lights are falling at equal angle on some surface, and then we get rings like this because the pattern is forming in all possible direction. If it is only forming in this direction, then we'll get dark bright in this particular linear straight line. But if the line is, the two waves are interfering at equal angle in all directions, the light is forming and interfering in all possible directions, say this is the center, and from this center at equal distance, the light is falling and interfering at equal distance from the center in all directions, then the dark bright pattern that we are seeing, we'll see it in all directions. That's why we see these concentric circles, which we call dark and bright rings. And for this particular experiment where we use plano convex lens, this rings that we get, we call it Newton's rings. So here we want to study the formation of Newton's rings in the air film. Here the setup is kept in air, and the medium here that is important is between. So as I said, we are using plano convex lens, means we have a small part of a convex lens and it is attached with a glass plate. So one is simple glass medium or whatever the medium is, and then we have a convex lens. This whole setup will give us the this kind of concentric circle ring pattern that we want. So this is the air film, this is the film glass plate which is, and just adjacent to it we have air between this. So this change of medium is important here to introduce the path difference, which will give us interference ultimately. So here the rings in the air film in between a plano convex lens and glass plate using nearly monochromatic light. This is another aspect. We will be using here monochromatic light because if we will be using white light, then instead of seeing this single color dark bright, we will be getting, since white light is constituted of various other colors, we will be seeing white light splitting. So we will be using monochromatic light. In the experiment, they had used sodium source, and using this we'll see how we can find out the radius of curvature of this plano convex lens. And recalling what we had discussed about a lens, that it comes from so we have say a glass sphere and then we cut a very small part of it, and this becomes our one part of lens, and the center of the sphere is say this, then this is the radius of curvature, and half of it is called the focus of that particular lens, right? Half focus is half of the radius of curvature of the lens. So we want to find out this value, radius of curvature of the plano convex lens, or we can, if we know the radius of curvature, then we can find out the wavelength of the light, monochromatic light that we are using in this experiment. We'll see how we can derive this formula so that we can find out the unknown values. So this is the setup. To just briefly discuss, this is monochromatic source, and we want to use an extended source, so we are keeping a convex lens here, which if it is at focal length, the source if it is at focal length of this convex lens, then it will, the lens will make it parallel. So these parallel beams, when fall or hit on this glass plate which is kept at 45 degree to the direction of incidence light, then these lights will reflect from it and fall on this plano convex lens setup that we have made here. When they will come here, since they are falling at 90 degree, so these incident lights are at 90 degree, yeah, they are at 90 degree, so they will not, like we know, if this is my surface and this is the normal, if incidence angle is something like this, then reflection angle from the law of reflection that we had discussed in second week or third week, angle of incidence is equal to angle of reflection. So here, if the angle of incidence is normal to the surface, that means the angle of incidence is 0 degree. Then angle of reflection will also be 0 degree. That means the incidence light is coming in this path, the reflected light will also travel back along the same path. So here, if since I said this plate is at 45 degree, if I make a normal to this plate, this angle is 45 degree. Okay, this angle is 45 degree. That means this angle of reflection will also be 45 degree. The angle of reflection also is 45 degree, and together they will make 90 degree. That means this incidence light is now changed, its path is changed by 90 degree, and since it's hitting this plano convex lens perpendicularly, after reflection also it will come back and trace the same path. So now in the interference here is happening between this light is coming, one part of it is getting reflected from this end. So if at the center the glass plate and this lens are joined, but if we'll move right or left from this center, then we'll see there is some gap. So this is varying thickness kind of glass plate situation. So here one part of light will be reflecting from this end of the this lens and going back. Another part of it will be reflecting after traveling this air gap, and it will be reflecting from this glass plate. So the path is same, I mean the direction is same, but here the distance traveled is some extra. Also, since one part is getting reflected from glass, there is glass air interface, which is this. Here it's glass, here is air, and there is another interface which is air glass interface, which is this particular point where above it's air, below it's glass. Now the again recalling that when the light is reflected from optically denser medium, which is happening for reflecting light from this particular point, when that happens there is extra phase of pi or extra path difference of lambda by 2. Because of this variation in path difference, the light is coming same, but the reflection is happening at two different points here, and there is path difference between them, due to which when they'll interfere, they'll go and interfere, and we'll be able to see what their interference pattern through microscope at this end. Here we'll be seeing, if we'll keep a screen, we'll see these kind of concentric circle, or we can use microscope, so we'll be seeing this kind of pattern. So this interference, now we'll see what is the formula for this. Okay. So right now we are seeing side view of our setup, and this lens and this glass plate, if we will be seeing top view, then we'll see something like this, because as I said, we are cutting a small part of a glass sphere. So from the top, when I see this lens, it will look like this. This is center of it. If say the thickness of this, by thickness I mean if this lens that we have kept, if T is its maximum thickness, okay, this I'm calling T, then let's denote it by T. Then the distance of this point from the center is, let's call it Rn. This will be the radius. If this small portion is T, then the distance from center will be R minus T, because this will be the radius. This is R minus T, this is radius. This T is the thickness of the air film or the gap. Now here this triangle, if you see this triangle I'm talking about, this is a right angle triangle, right? Here if you see, apply Pythagoras rule, then we can see R minus T whole squared plus Rn square will be equal to R square, right? Now when you will expand this, we will get R square plus T square minus 2RT plus Rn square is equal to R square. Now the radius of curvature of this from which we have cut this lens, usually that is part of a very huge sphere, so thickness here is very small compared to this radius of curvature of this lens. So we can ignore this, and then we get here R square will be cancelled, and this Rn square will be 2 times R times T. That means T will be Rn square divided by 2R. So thickness we obtained in terms of radius of curvature. Now as we were talking about the path difference, so the path difference here is the extra path that the another one ray is reflecting from this point, another ray is reflecting from this point, and it will have it is traveling this extra, it's coming here T, then going back, that means 2t. And also since refractive index is different, so we'll multiply it with mu. So this extra path it's traveling, along with that it's also taking since it's reflecting from an optically denser medium, so we know pi is the extra phase difference, or pi times lambda by 2 pi, which is the lambda by 2, which will give, that is the extra path difference. So this is we are getting because it's traveling. If I show it here again, one part is reflecting from this, but since it's reflecting from rarer medium, it will not have any extra path difference. But the another one is coming, traveling this air gap, and then reflecting from optically denser medium. So it will have this extra length that it's traveling, coming down and going up, that plus lambda by 2. So total path difference will be 2 mu t plus lambda by 2. Okay. Now condition for bright fringe, as I just told in previously when I was explaining, this is the path difference, and to get bright fringe we should have it multiple of lambda. But this lambda by 2, when it will come to right side, we'll see we are getting n minus half lambda. So this now becomes the condition for getting the bright fringe. And similarly for dark fringe, earlier it has, to get dark fringe, the path difference should be integral multiple of lambda, odd integral multiple of lambda, right? That's why we write n plus half multiplied by lambda. But this lambda by 2, it will come right side, and we will see finally we are getting 2 mu t is equal to n lambda. And for air film, here we are talking about, for air refractive index is 1, so 2t will become n lambda for dark fringe, and 2t become n minus 1 or n plus half lambda for bright fringe. So this is how the condition becomes in terms for this Newton's ring experiment. Okay, so this was about the experiment. Here we'll, in the experimental setup, again for the experiment, to watch the video where the professor has explained the and demonstrated very nicely the whole experiment. So here we will be taking different fringes, and we will try to take, so we'll be seeing some pattern, dark, bright, dark, bright. So we'll keep our cross wire somewhere here at the one end of this circle. One time we'll keep it here, another time we'll keep it here. So this is what we mean by left. We are taking left reading, means we are keeping our cross wires at left edges of these circles, and then we'll move it to right edges of these circles, and then we'll note down the reading. After that we'll take this R1 minus R2 by subtracting these values and taking square of them, diameters. So this we'll get these readings. And when we'll plot graph between this dn plus m1 square minus dn plus m2 square as plot of m1 and m1 minus m2, here m1 minus m2 is this 10 minus 1, which will give us 9, then 9 minus 1, which will give us 8. Similarly, like this, we'll get 4, 3, 2, 1, okay, and 0. So when we'll plot this versus m1 minus m2, m1 minus m2, and here we have this whole thing here, we'll see a straight line. When we'll take slope of this, it will be equal to 4 lambda r. So 4 lambda r will be equal to slope of this, and when we will be able to find out slope, then lambda, if r is known, then we can find out lambda if we have used unknown source of light, and radius of curvature of lens is known, then we can find out the wavelength of that particular light. Or in case we know the wavelength but we don't know radius of curvature of that lens, then we can find out that as well. It will be 4 times lambda. So this was the procedure and what we wanted to find out from this particular experiment. Main thing, first thing is to see the Newton's ring experiment, and then to find out the unknown. Another experiment that was discussed was Michelson interferometer. In this, we wanted to determine the wavelength of laser source. So again, as in previous experiment also, we were trying if radius of curvature is known, then we can find out wavelength. Similarly here also, if we know some, we'll see what is the dependent variables, then we can find out wavelength of laser source if it's unknown by observing the fringe obtained in Michelson interferometer. So Michelson interferometer also we get to see rings like this, but unlike the air film or varying thickness kind of film that we were using in Newton's ring experiment, here we are using some mirrors instead of lenses. So let's again briefly discuss the setup. We have a laser source and we are using a convex lens to get extended source. Okay, otherwise laser we know is almost monochromatic and goes almost parallel. So to get extended source, we'll use a convex lens which will diverge them a little bit. Then we have kept a half silvered glass plate. Why? Because we want to make some, again we are here using a single source, then it cannot give us interference until we do some change in uh, its path difference. So here what will happen when we keep a half silvered glass plate? Half silvered glass plate, if it's completely silvered, then all the lights falling on it will be reflected. But if it's half silvered, that means some of it will be reflected, some of it will be transmit or refract. So when the light comes from here, it passes through laser, gets diverged, means we are getting extended source of light. When it falls here, some of it will go to mirror M2, some of it will go to mirror M1 straight, will pass through it. The one which is going here will again reflect from here because it's completely polished, so it all will reflect back, and then from here it will come down back here. Now the one which had got reflected from this silver glass plate, half silvered glass plate, will go and hit mirror M2. Since it's completely polished, it will not transmit, but all of the one hitting here, all of the one which were hitting here will come back and pass through here. Okay, and when whatever light rays, the one coming from here, if you see the distance is same, this is the same distance that two all the lights are traveling, then some go this path, this, and come here, this goes travel here, then double of it, and then come here. If the distance between these two are same, then we can see all the distance are traveling, they are traveling is same, but again the path difference of lambda by 2 will come here, because the one which is getting reflected from this side, okay, it is outside its air, this glass plate is optically denser, so the one reflected from here will have path difference of lambda by 2. So even if the distances d1 d2 are same, but there will be path difference between these two coherent sources and they will interfere, and we'll see rings. If we consider this center incident ray, then we'll get a pattern here. But if they, since I said we are using extended source, they will be at some angle theta, and then we'll be getting final inclination on the screen, and they will form a ring around this. Okay, so here path difference additional, even if this d1 d2 is not same, that means we have some path difference or d1 minus d2. Along with this, there will be path difference of lambda by 2 because of reflection from optically denser medium. Okay, fine. But I think when it's coming, okay, maybe this, sorry, is not there here. You see why? Because first it's reflecting from here, but after that it's passing, whereas this ray which is just passing, after that when it's coming here it's reflecting. So I think for both the rays the reflection from optically denser is happening. That means for this case maybe this won't happen, but okay, in that case just d1 minus d2 is the situation here. So 2d cos theta, where d is the difference between d1 minus d2. So 2d cos theta, m lambda is the condition for bright fringe, we know. Okay, now if we introduce a biprism in it, which was the second part of this experiment, to determine the base angle of a Fresnel's biprism by introducing it in one of the arms of Michelson interferometer. So in one of the arm we are introducing this biprism, and then we see what is the, we have to actually find out base angle. Now we'll see how. So when we introduce this, so the ring will shift, when we'll be seeing the dark and bright fringes, if we introduce any path difference, then we'll see these fringes will be emerging out or going in, kind of like they'll be shifting. So when we do this, this is the path difference will become 2 mu minus 1. Why? Because if the thickness of this biprism at this particular point from which the light is passing, the thickness is t, and the light is passing through it once, that means t mu t. Why? Because the refractive index is different. So once the additional path difference will be mu t when it's going in one direction, then it's coming back, that means again it's traveling mu t different. So this is the additional path it's covering. So the path difference will be 2 mu t minus 2t. Why? Because if when it was not there, that time it was covering this whole distance. Now that out of all that distance, 2t is not there, 2 mu t is there. So that's why the path difference becomes 2 mu t minus 2t, and when we will take out 2t common from it, we'll get 2d multiplied by mu minus 1. Alright. So for number of fringes which appear or collapse, if say they are m, then the path difference multiplied by m lambda, sorry, it will be equal to m times lambda, and from this we can see the thickness of this biprism, we will get m lambda divided by 2 mu minus 1, and from this relation this angle, so this is the biprism. Okay, one part of it, if we see, this is phi angle, or the angle of prism, or base angle we call it angle of prism, or also base angle. So to find this, it will be t by l. Now t is this by l will give us the angle of prism. So this, based on these, we will be doing some questions. Okay, this is the same thing. Apart from these two experiments, so we had started, the lecture video we had seen for this week, that the discussion had started to understand what to. So till now we were discussing, we had discussed dispersion through prism and did a lot of experiments based on it. Then till now we were discussing interference phenomena, based on which we did various experiments, especially like in this lecture, in this discussion as we are discussing with Newton's ring experiment and Michelson interferometer. After interference, we want to study another phenomena, which is diffraction of light, which means bending of light. So usually we say that light travels in straight line or straight path, but that's not the case all the time. There is some particular situation where the light deviates from straight path, and when this happens, this phenomena is called diffraction of light. Light diffracts from its original path, and this happens when that obstacle by which it's deviating from its path, that dimension of that obstacle is like say size of that thing is when it's comparable to the wavelength of light, that time only this diffraction happens. And that's why we see X-ray diffraction phenomena that we use to study the structural properties of any material that we prepare, because X-ray have some wavelength of around 1 to 3 angstrom, which is also the size of atoms, and that's why we see diffraction through those atoms of X-rays, and then we are able to see the atomic properties. So this is what we mean by diffraction of light, and this happens when the size of obstacle is, or size of that thing by which it's diffracting, is of comparable size to its wavelength. Now under diffraction we'll be discussing a lot of things, but since only one lecture video was there, I think most of it, the things under diffraction of light topic will be covered in next following week. So here just what we were introduced to was Huygens principle, which tells that each point on a wavefront of light, a wave, can be treated as a new source of wave. What we mean is, if this is my source of light, and if we know light has been shown to have wave nature or particle nature. So here if we consider this is the source of light and it's traveling in form of wave, then every point on it, on this wave front, can be treated as another source of wave, and these are called secondary wavelets, as you can see. So this is the wave front traveling, and then if we take one direction and this is one point, that point can be considered a new source of wave. Then there will be this another point. Okay. This will be another point that also can be treated as new source of wave. So this is Huygens principle, and we see what things we get by this assumption. And thus interference among these secondary wavelets also is called diffraction. And then we were discussing Fresnel diffraction and Fraunhofer diffraction. The basic difference is that under Fresnel diffraction we consider either the source, something like this, either source or the screen, or both are at finite distance with respect to the obstacle or the aperture. Here we have a small aperture through which these straight lines you see, these we are representing is the wavefront, which is plane. Okay, but when it's passing through this aperture, they are bending through this obstacle or this aperture, and instead of just going in this straight direction, now we have light traveling in these other directions as well. This is only happening because the light is bending through this aperture. So in Fresnel diffraction, the source or screen or both are at finite distance. Whereas in Fraunhofer diffraction, which will be the mostly discussed thing in the coming lectures, we have source and screen or both at infinite distance, so that we can get extended source, or we can get parallel rays of source. So the Fraunhofer diffraction, as I said, source and screen are at infinite distance, means our incident rays on the object are parallel, and diffracted rays for image formation on the screen are also parallel. So this was just the introduction. Further discussions will be in following weeks. Now I think we can start discussing the numericals based on this. Let me just save things till now. Okay, it should not come here. Recording is going on, everything is fine, it's okay. Yeah. So let's start with the numericals, which are more important in this discussion session. So first problem is, in Fresnel's biprism experiment, this if you remember we had, I don't know I have here or not, Fresnel's biprism experiment. Yeah, this here it is. So this we had discussed last week, that we, as this, why we use this, to get coherent sources. So from a single source, when we use a prism like this, we get virtual image of two different sources. So thus the waves that are going after refraction from single source, when they meet, like when they travel in this direction, it seems they are coming from S1, S2 virtual sources, and thus they are coherent and they will interfere to give us interference pattern. So this is how the Fresnel biprism looks, and we had also discussed experiment based on it. So now The question is based on this. I just showed you so that we can recollect what is happening. It's getting okay. So the first question is, in Fresnel's biprism experiment, the biprism is illuminated by a sodium lamp. So we have given the value of what happened again. So we have lambda. We are using a sodium lamp, wavelength of 589 nanometer. Eyepiece is at a distance of 1 meter from the slit. So we have some, say, some source. We have some slit. It's coming out like this, and then we have the bright prism kept, and there is a screen, or where we have eyepiece maybe, through which we are observing the pattern. So here we have been given the wavelength of the light, monochromatic light, and also that eyepiece is at a distance of 1 meter from the slit. So the distance of the eyepiece or the screen from the slit or the source is 1 meter. Okay. A convex lens inserted between biprism and the eyepiece. Means here now we are introducing a convex lens to give clear image of coherent source. Coherent source, I told, the lights will be refracting from here, and we'll be seeing as if they're coming from sources S1 and S2. Okay, so the image of coherent source in the focal plane of eyepiece we are getting if the source images are 0.2 centimeter apart. These source images are 0.2 centimeter apart, which we also denote by small d. This we denote by capital D. And in one case and 0.32 centimeter apart in the second case. Okay. Calculate the width of interference fringes observed on the screen. So when we are given these different what we say source image distance, then we are given two different cases. Then to find out d, this is the relation we use. Okay. Now we know, when we know the small d, capital D, and lambda, then ultimately we want to find out, calculate the width of interference fringes. That means beta. Now we know beta has relation lambda d by small d, and here we know lambda, which is 589. This is given in nanometer. Our final answer is in centimeter, so let's convert this. Nanometer means 589 times 10 to the power minus 9 meters. Now to put this in centimeter, it will be 589 times 10 to the power minus 7 centimeter, because 1 meter has 100 centimeter. So it will be 10 to the power minus 7 centimeter. 589 times 10 to the power minus 7 multiplied by the distance is 1 meter. Again in centimeter it will be 100 centimeter. This will be 100 divided by the small d, which I said will be root of d1 by d2. Let's calculate this square root of d1 by d2. Let's take this. I'll use my calculator for this. Okay. So d1 is 0.2 multiplied by 0.32. The value is 0.064, and I'll take root of this. Will be 0.253. 0.253 centimeter. Okay, I'll put that value here, 0.253, and the final answer will become 589 multiplied by 100 divided by 0.253. will give and multiply. It will be 232,806.32 something times 10 to the power minus 7 centimeter. When I do this, it will become 1, 2, 3, 4, 5, 6, 7. That means 0.0233. If I just want to keep them to 4 decimal digits, then this will be the answer. So here the correct answer that is matching is option A, that is 0.023 centimeters. So option A is the correct answer here. Okay, I have to move it. Yeah, now the next question. So the next question is that again it's based on Fresnel's biprism experiment, and here we have been given the fringes of width. Okay, so here we have given beta, which is 5 times 10 to the power minus 4 meters, are observed with the light of wavelength. Wavelength is given, which is 500 nanometer at a distance of 0.9 meter from the biprism. Okay, so the situation is like this. We have a source, we have biprism, and we have screen, I think, or wherever we are observing the pattern. Now they have given the distance of 0.9 meter. This is the distance between from the biprism. This distance is from the biprism, which is 0.9 meters. Okay, from this, and refractive index of the material of prism is 1.5, and at this biprism is placed at a distance of 0.1 meter from the slit illuminating the biprism. Slit means this our source. This is biprism is kept at a distance of 0.1 meter from the source. So that means this distance between source and our screen, or wherever where we are observing the pattern, this distance becomes 0.1 plus 0.9 meters, that is 1 meter. Okay, that means 100 centimeter. Now we have to find out the acute angle of the prism. That means this angle, alpha. We need to find out angle of the prism. So for this, we know beta. Fringe width, first we'll see what values we can obtain. The fringe width depends on lambda, distance between source and screen, and the distance between the virtual images S1, S2. So here also we know D, that we had seen, D is given by 2a mu minus 1 alpha, where alpha is the angle of the prism, a is the distance between slit and the prism. The slit and the prism, this is the distance. So when I substitute this here, we'll see beta will be lambda d divided by 2a mu minus 1 times alpha. Now substituting these values, and okay, or let me rearrange, because alpha is what we want to find out. So it will be lambda d divided by 2a times mu minus 1 times beta. Okay, now when we substitute these values, let me use another slide, or let me write here. So lambda is how much? Lambda is 500. Let's put everything in meters. 10 to the power minus 9, then it will become in meters, and multiplied by, or let me write here, there's not enough space. So alpha will be lambda d. Lambda is 500 nanometer, that means 500 times 10 to the power minus 9 meters, and d is 1 meter divided by 2. A is 0.1, right? A, which is the distance between the source and the biprism. So this will be 0.1, and mu. So mu has been given to be 1.5. So 1.5 minus 1 times beta. Beta we have been given to be 5 times 10 to the power minus 4 meters. 5 times 10 to the power minus 4 meters. So everything is in meters. This one we'll calculate, we'll get 500, and this 10 to the power minus 9 divided by 10 to the power minus 4 means we'll get 10 to the power minus 5 divided by 2 times 0.1 times 1.5 minus 1 means 0.5. Okay, when we'll calculate this, we'll be getting 500 multiplied divided by 2 divided by 0.1 divided by 0.5. It will be 5,000. Did I forget something? Am I forgetting something? Oh, this 5. I forgot this 5. That's fine. Okay. So this will become, yeah, right, 500. This I took care of. Then in denominator we have 2 multiplied by 0.1 multiplied by 0.5 multiplied by 5. So this will be 100. Okay. This will be 50. 50 divided by 5. 1.1. 50 divided by 0.5. 50 divided by 0.5 is 100. Divided by 0.1 is 1000. Getting 1000 multiplied by 10 to the power minus 5. This angle will be in radian. This 5 means 1, 2, 3, 4, 5. Means 0.01 radian will be the correct answer. So the option correct here is 0.01 radian is the 0.01 radian is the correct answer. Option A is correct. Now moving on to the third question, which is our next question. It's on interference fringes again by Fresnel biprism. Just to tell you again that these questions first I am discussing with, these are from the previous year when experimental physics 2 course was being conducted. These questions were put as assignment part, so that's why I think they are very much relevant and will be helpful for you guys to solve. So the similar pattern questions you will be seeing in your exams as well as in your this week's assignments. Okay. So the third question is again on Fresnel biprism, and it says that interference fringes are produced by biprism in the focal plane of microscope. So instead of screen, here we are directly keeping a microscope, a focal plane, which is located at a distance of 1 centimeter from the slit. That means our source and screen or microscope are at a distance of 1 meter, and here our biprism is also there. 2 images of coherent sources are produced by convex lens placed between microscope and the biprism. Okay, if these images are 4.10 mm apart, 4.10 millimeter apart in one case, and so D1 is this, D2 is, we don't know, some distance B, millimeter or something. We have to find out this, what is the value of this. Fringe width is 0.175 millimeter and wavelength is 589 nanometer. Now we have just seen, when we know D1, D2 like this, then we can find out D, which is square root of product of D1, D2. That means D here, because we will use for finding out fringe width, the formula is this. D is D1, which is 4.10 multiplied by B. And all these values we know. So D will be lambda d by beta, and d is square root of 4.10 times b is equal to lambda by beta. That means finally we have to take square. So 4.1 times b is equal to lambda square d square divided by beta square. Now lambda square is 589 nanometer. Okay, let's first calculate everything and then we'll take square of it. So this is 589 nanometer. Our answers finally are in centimeter. So we'll convert it into centimeter. It means it will be 10 to the power minus 7 centimeter multiplied by d. d is 1 meter. It means 100 centimeter divided by beta. Beta is given 0.175 millimeter. 0.175 millimeter. If I put it into centimeter, then it will be 10 to the power minus 1 centimeter. No, sorry. Yeah, it's correct. Millimeter to centimeter, when I'll convert, it will 10 to the power minus 1. And then we have to take square of all this. So first let me calculate what I'll get. 589 multiplied by 100 divided by 0.175 is 33657.43. Now the exponents will be, here I have 10 to the power minus 1, here it's minus 7, so this will be plus 1. 1 minus 7 is minus 6 and whole square. This will become 1, 2, 3, 4, 5, 6. That means 0.3366. Let's make it. And square of this thing. 0.3366. 0.3366. Yeah. This will be 0.1133. Okay. Now this is actually equal to 4.1 times b. So b will become 0.1133 divided by 4.1. This should be getting in centimeters. 4.1133 divided by 4.1. This will give us 0.0276 centimeter. Is there some mistake did we do somewhere for this 100? I had multiplied or not? I think I did. Did we make a mistake here? This 4.10 was in millimeter. I'm sorry. This 4.10 was in millimeter, means if I convert it into centimeter, it will be 0.41 centimeter. So correcting this here, okay, this will be 0.41. 0.41. 0.41. Then I will get 0.1133 divided by 0.41. That means 0.2763. 0.2763 centimeter would be the correct answer. Okay, so they have only taken up to 3 decimal digits. So this answer D is the correct answer here. We just need to remember these particular formulas and then all the questions we can solve easily. And also we need to be careful with the conversion of SI units because the values are given in different units. Wavelength is given in nanometer, the difference between source, that is slit, and screen is in meters, then other things are in centimeters. So we need to take care of the unit conversion and then formula, and with these things we will be able to solve these numericals. Okay, next question, which is the fourth question. The question is the obtuse angle of a prism is 176 degree. Okay, this is again, it seems like Fresnel biprism kind of question. So the obtuse angle of a prism is 176 degrees. A slit illuminated by a monochromatic light of wavelength 571.5 nanometer. This is the wavelength 571.5 nanometer of the monochromatic wavelength light we are using for this experiment. A slit illuminated by this monochromatic light of wavelength is placed at a distance of 0.1 meter from the biprism. So this is our source or the slit. Okay. And then we have a biprism kept, and then we have a screen. The distance between the source and biprism is 0.1 meter as given. The angle, obtuse angle here, so actually biprism I am drawing like this, but actually the biprism looks like this. These angles are very small. This is the obtuse angle here, because here all the angles look same, but actually it's looks something like this, biprism. So the obtuse angle is given to be 176 degree, means this angle we are talking about, it is 176 degree. So this one angle we know, we call it a base angle or acute angle of this prism. That will be what we know, in a triangle all the angles are 180 degree, right? One of the angle we know is 176 degree. Also these two angles are equal. Let's call one angle alpha. So out of 180, this should be 0, because this 176 plus alpha will be 180 degree. So when I'll try to find out, this will be 4 degree plus y plus minus 2 alpha is equal to 0. That means 2 degree plus alpha is equal to 0. It will be minus, this will be minus, all this is a minus. Why I am getting this? Because 180 degree here is made up of 176 degree plus alpha plus alpha. So when all these things will go left hand side, they'll be in minus. Okay, so alpha will be 2 degree. This we found just now. Okay, the distance between the biprism and the screen, distance between biprism and the screen is 1 meter. That means the distance between source and the screen becomes 1.1 meters. Calculate the distance between two consecutive dark fringes. Okay, so we have to see nth dark fringe and n plus 1th or n minus 1th, anything. Let's say n plus 1th dark fringe. We'll see at with what condition they will be formed, and then we have to find out the distance between the distance between two consecutive dark fringes. Now you should understand what do we mean by here. In Fresnel biprism we get fringes pattern, dark bright, okay, and when we are talking about consecutive dark fringe, between them distance, the distance between two consecutive dark fringe or bright fringe, what we mean is, say if this is the nth dark fringe, this is the n plus 1th dark fringe, this is the n minus 1th dark fringe, then distance between them means fringe width of bright fringe. Similarly, if I am talking about the distance between two consecutive bright fringe, then between them is a dark fringe. That means I am talking about the fringe width of the dark area. So here when we are talking about distance between two consecutive dark fringes, means I am talking about the distance between two consecutive the fringe width of bright fringe. Anyway, the dark fringe bright fringe width are same. So basically what we are talking about is the fringe width of the pattern. This is what we want to find out. Distance between the consecutive dark fringe means the the fringe width. This is what we have to find out in this question. Refractive index of material is given, which is 1.5. Now let's start solving this question. We need these details. So the fringe width depends on wavelength, the distance between source and the screen, and the distance between these two sources, virtual images. Okay, virtual images or virtual sources that we call it. Now when we'll calculate this, this D is not given here. Okay, we have not been given the distance between the virtual sources. How we'll find out this? Again recall, we had got to know one formula, which is this distance is given by 2a multiplied by mu minus 1 times alpha. Alpha is the angle of prism that we have just now found out, and a is the distance between source and biprism, which is 0.1 meters. Our answers are also in meters, so we'll keep it everything in meters. So let's calculate D. 2 times this is 0.1 meters. Refractive index has been given to be, this is 1.5. So this is 1.5 minus 1 times alpha, which is 2 degree. Now we cannot keep it in degree, we need to convert it into radians. So 1 degree, if I want to convert it 1 degree into radian, if I want to convert, then 1 degree multiplied by pi by 180 degrees. Okay, this will give me so 1 degree will be like this in radian. Now I have to convert 2 degree. So this becomes pi by 180 in radian. 1 degree is pi by 180 radian. So 2 degrees will be 2 times pi by 180 radian. That means pi by 90 radian. So this is the value, whatever is we'll calculate, that will be the value in radian. So D will be 0.2 multiplying these two. Then 1.5 minus 1 means 0.5, and 2 degree means pi by 90 radian. This when we'll calculate, we'll get, we calculate this will be 0.2 multiplied by 0.5 multiplied by pi, okay, divided by 90. This will be, D is 0.0035 meters. Okay, now putting this value here, okay, beta is what we need to find out. Lambda we know, lambda is given to be 571.5 nanometer. 571.5 nanometer. Nanometer means 10 to the power minus 9 multiplied by D, which is 1.1 meters. It's little slow. 1.1 meters divided by this D, which is 0.0035. Now when I evaluate this, calculate this, 571.5 multiplied by 1.1 divided by 0.0035, this will give us some value, and when I'll take care of, okay, let me write 179,614.2857 multiplied by 10 to the power minus 9. When I take care of this 10 to the power minus 9, it will be 1, 2, 3, 4, 5. 1.796 times 10 to the power minus 4 meter. So our answer is 1.796. So here they have only gone to first decimal digit. So when we'll round off 1.796, we want to round it off to first decimal digit, then it will be 1.8 times 10 to the power minus 4 meters. So the correct option that matches with our answer is this, option B, 1.8 times 10 to the power minus 4 meters is the correct answer. Option B is the correct answer here. Sorry. Okay. Now next question, question 5th. plano convex lens. Okay, so now the questions numericals are starting based on, okay, just to confirm that recording is going all right. Yeah. So now the questions are starting based on the Newton's ring experiment that we discussed. Okay. So plano convex lens of radius of curvature 1 meter is placed on an optically flat glass plate. This kind of setup touches at this point. Uh, it is illuminated by extended monochromatic source. Assume that the point of contact is perfect. Diameters of 15th and 5th dark ring in the reflected light are this. Okay, this and this. So diameter of 15th dark ring is 6 times 10 to the power minus 3 meters, and diameter of 5th dark ring is 3 times 10 to the power minus 3 meters. So how we talk about diameter, at the center we'll see something like this. Either it will be dark or bright, usually it's dark, but it could be changing. Then we have something like this, and this will be dark or bright, a particular width. Then again there will be another, I'm not able to draw these circles properly. Okay, again either this will be dark or this will be bright, a particular width. So this is the center. This we call the first ring. This is the second ring. So diameter, when we are talking about, we are taking this here to here. Then diameter of second ring means this. Okay, just to clarify. So diameter of 15th dark ring is this. Diameter of 5th dark ring is this. Okay, now we have to calculate the wavelength of light used. Again, as we were discussing, that either if we know radius of curvature, we can find out wavelength, or vice versa. So here we have been given the value of radius of curvature. Now we need to find out the wavelength. Now recall the formula that lambda is given by d n plus p square minus d n square divided by 4r multiplied by this. This p is what? Like if you remember in the experiment what we were seeing, we were plotting a graph between this m1 minus m2, right? The 5th order or 10th order, the difference between them, and then d n plus m1 and d n m plus m2 squares we were here, then we were getting straight line. So that is the same thing. Dn plus p square minus dn square divided by 4r. Here instead of m1 minus m2, the difference we are representing as p. Okay, so that is the same thing. So if I write this as d 5 plus 10, then you can see this is 15th order, this is 5th order. So the number of fringes in between is 10. So p is 10. Now when I put the values, this will be, answer are in nanometer. Okay, this is in meter right now. We need to convert it into nanometer. Maybe we can do it at the end. So 6 times 10 to the power minus 3 square of it minus 3 times 10 to the power minus 3 square of it divided by 4 times r is, these are in meters, r also let's keep it in meter, and p is 10. Then okay, calculating this, 6 square means 36 minus 3 square means 9, 36 minus 9, and this 10 to the power minus 3 square means 10 to the power minus 6 divided by 40. This of 36 minus 9 means 27. 27 divided by 40 and multiplied by 10 to the power minus 6. Right now it's in meters. 27 divided by 40 will be 0.675 meters. Oh sorry, there is 10 to the power minus 6 also. Now when we'll convert it into nanometer, because our answers are in nanometer, this will be, I can write it here, from meter to nanometer means 0.675 times 10 to the power minus 6 multiplied by 10 to the power, 1 meter is 10 to the power 9 nanometer. Then this will become 0.675 times 9 minus 6 means 3, 10 to the power 3 nanometer. 1, 2, 3, 6, 75 nanometer. This is our answer. Let's see which option matches this. So option C is, which is 675 nanometer, is the correct answer. So for this Newton ring experiment where radius of curvature and these diameters are known, then we can find out the wavelength, which we are getting to be 675 nanometer. So the C option is the correct one. Now the sixth question, again it's on Newton's ring experiment. We have a plano-convex lens of radius 1 meter. Radius is 1 meter. See, this is what I was telling while I was telling that uh, we can assume the thickness, neglect the thickness when we were opening the squaring brackets, because the radius is 1 meter, whereas thickness is only few centimeters max to max, like 0.1 centimeter, 0.01 centimeter, something like that. So that's why we were assuming it to be is easy, like okay to neglect it. A plano-convex lens, okay, coming back to the question, plano-convex lens of radius 1 meter is placed on an optically flat glass plate. Again the same thing. Okay, they are touching actually. Yeah, I should not draw like this. And they are touching, yeah, like this. The space between lens and the glass plate is filled with a liquid. Okay, so usually we were talking about that this setup, I mean this is filled by air, but right now, as told in this question, it is filled by a liquid. After inserting the liquid, the diameter of fifth dark order ring changes to this. Okay, calculate the refractive index of liquid. You need to find out what is the refractive index of the liquid when the wavelength of light used, that same source of light we'll keep on using, but when we change the setup, the gap between this thing from air to this liquid, the diameter of fifth dark order ring changes to this. Now let's see. Yeah, so here what's happening is, when a ray of light passing through rarer medium, no sorry, medium having refractive mu, its wavelength changes. We know refractive index is function of wavelength always, and frequency, actually we also define that speed of light in air or vacuum to speed of light in the medium, whatever it is in that medium. And we know that velocity is this, but this doesn't change with the refractive index because it's mu, which is frequency of the light. It depends on the source. So what changes is wavelength. So refractive index is this wavelength in air to wavelength in the medium. Okay, that means wavelength in the new medium will be lambda divided by mu. Lambda, that is wavelength in air, to the refractive index of the medium. Now we know the formula that this n lambda r divided by mu, this formula we had got, if you recall, we had obtained 2t is equal to dn square by 4r. This we had obtained. The thickness depends like this. Okay, this was subscript. I'll show you just to recall what formula I'm talking about. When we were talking about the theory or working principle to obtain the working formula of Newton's ring experiment, here, yes, this thing, if you see, we had we had taken top view of this lens system, and then we found out 2t is dn squared by 4r. This is the formula we'll use right now for our question. Yeah, just a minute. This is the formula we are talking about. Okay, 2t is dn squared by 4r. dn is double of radius, so I can write it as 2rn and the square of all this divided by 4r, means this will be 4rn square. This is the radius of nth ring divided by 4r. R is the radius of curvature. This will be cancelled, so I will be getting t is equal to rn square divided by this 2 will come to denominator, it will become 2 times r. This is the thickness of the gap between the lens and the plane plate at the distance where the nth ring is forming. Okay, now there is another thing, that for getting here we need to obtain what, dark or bright fringe we are talking about. Here we are talking about dark order ring, fifth dark order ring. For getting dark nth order ring, we know the path difference 2 mu t plus we know lambda by 2 will be extra. That's why the condition changes and becomes something like n lambda for dark ring. And from this, when I'll put the value of t, it will be 2 mu rn square divided by 2r is equal to n lambda. From this, rn square will be this 2 in denominator and numerator will be cancelled. We'll get n lambda by mu. So using this particular formula we'll use here to find out that. So we have seen this part, that mu is, or this lambda in this medium will be lambda in air divided by refractive index mu. Now further this relation we found out. Now this n lambda, okay, so refractive index, or did I miss something? Okay, so from rn square it will be 2dr also. So here my formula becomes, I think if I compare, it will be this and this. It will become rn will be n lambda r for nth order dark ring will be this. Here, okay. So from this, now diameter is 2 times rn. So diameter will be 2 times rn. So dn square will be 4n lambda r by mu, or mu is equal to 4n lambda r divided by dn square. Now we'll substitute all the values and we'll get mu, which we need to find out, for that nth order is fifth, r is 1 meter, lambda is given to be 589 nanometer. Yeah, 589 nanometer. 589 nanometer. Our final answer is in, oh, it's refractive index also. We'll just keep everything same. 10 to the power minus 9, I think we can do, because 4n lambda This is R is in meters, I think. R is in meter. So okay, we'll keep everything in meters. Then dn square. Now the diameter of fifth order dark ring is given to be 3 times 10 to the power minus 3 meters, and we have to take square of it. Now when we'll solve this, we get 4 times 5 times 589 divided by 9, that is 1308.88 or 89, 10 to the power minus 9, 10 to the power, this will be minus 6, so plus 6. Minus 9 plus 6 is minus 3. 1308.89 or 88, 10 to the power minus 3. This will become 1.3. So this will be the refractive index of this material, and our option matches option A, 1.31. So if we have to take up to second decimal digit, then we can make this. Actually, when this we take care of power minus 3, then the decimal point will shift to 1.30889, something like this. If I have to take up to 2 decimal digit, then it will be 1.31, and the correct option that matches is option C. Next question is again on Newton's ring. Here wavelength of the light is given 600 nanometer. A drop of water having refractive index 1.34 is between the lens and the plate. We are keeping drop of water whose refractive index is 1.34. The diameter of 10th order dark ring becomes 6 times 10 to the power minus 3 meter. Calculate the radius of curvature of the lens. Now we have to calculate R. Again, the formula that we had found out, Rn square divided by 2R, this is one relation. And when I substitute this, because we have to take care of dark ring of 10th order, so 2 mu t will be equal to n lambda, and this t 2 mu Rn square divided by 2R is equal to n lambda. Here n is 10th order actually, and we need to find out radius of curvature. That means this mu Rn square by R is equal to n lambda. From this, if I rearrange, I'll get radius of curvature is equal to mu Rn square divided by n lambda. Substituting the values, refractive index is given to be 1.34. Diameter is given, then we can change it to radius by taking half of it. That means 6 divided by 2, which is 3, times 10 to the power minus 3, square of this divided by n, which is 10th order, lambda, which is 600 nanometer, and to the power minus 9. So this is also in meter, correct? This is also in meter, so this is also correct. Now when we calculate this radius of curvature, we have to find out radius of curvature. Okay, I understand. So when we calculate, we'll get 1.34 times 9 divided by 6. We'll get 0.00201 multiplied by 10 to the power minus 6 divided by 10 to the power minus 9. This will become 0.00201. This 9 minus 6 will be 10 to the power 3. These are in meters. This will be 1, 2, 3. That means 2.01 meters. The option that matches with our answer is option B, 2.01 meters. Okay. So now the next question, just question 8. Here again this is on Newton's rings experiment. The question is, in a Newton ring experiment, we have to calculate the thickness of air film. So this is our setup, this is touching. This is the air film we are talking about, this gap. We have to find out the thickness of air film. As you can see, the thickness is varying, but we have to find out the thickness at the position where 10th order dark ring is produced. So at the center will be dark, then bright, then dark, then bright. So consecutively, alternatively, we'll be getting dark and bright fringes. Where we'll be getting 10th order dark ring, we have to find out the thickness at that particular place. Wavelength here we have to consider 590 nanometer, and final answers are in meter. We'll consider that also. Light is incident normally. Okay, so here again using our formula, 2t will be Rn square divided by capital R. Now for dark ring, we know the path difference condition. It should be like this. That means 2t, because we are talking about air whose refractive index is 1, so this will become 2t is equal to n lambda. Now t will be n lambda by 2, and this will be n is which order? 10th order. Wavelength is 590. We have to find out in meters, so we'll convert this in meters, divided by 2. So this will be 5 times 590 times 10 to the power minus 9 meters. This will be 590 times 5, that is 2950. 2950 times 10 to the power minus 9 meters. Since the answers are in decimal, we'll take 2, 3. This will be 2.95 10 to the power minus 6 meters, because we are only moving it by 3 decimal digit. And our answer that matches is 2.95 10 to the power minus 6 meters. This is the correct answer. Answer is the correct option. Next question is in a Michelson interferometer. So now we were doing till now on Fresnel's biprism and Newton ring. Now the question is on Michelson interferometer, where we are using the mirrors. So in this question, we are using a Michelson interferometer. When the movable mirror moves through a distance of 0.233 mm. Okay, so the distance that we are moving it, the one arm or the one mirror, is this much, and the number of fringes that get shifted is 790. We have to find out wavelength of the light used. So in the formula that we had derived, we had seen this. Then when we move or shift one of the arm, the number of fringe shift is given by 2 multiplied by the distance by which we have moved one of the mirror divided by lambda. Okay. From this formula, the lambda we can find out as 2 multiplied by lambda d divided by delta m. So the values when you will put delta d is 0.233 millimeter. Our answers are in nanometer. So wait, let me put this millimeter to nanometer. When I'll change, let me do it properly. So So this delta D, which is 0.233 millimeter, it will be 0.233 in meters. It will be 10 to the power minus 3 meters, and in nanometer it will be, or I can find it in oh sorry, delta M is 790. This is in meters, later I'll change it into nanometer. So lambda will be, let me calculate, 2 times 0.233, okay, divided by 790, that is 0.0005899 times 10 to the power minus 3 meters. In nanometer it will be, meter to nanometer वाला when I'll convert it will 10 to the power minus 9 nanometer. That means meter to nanometer plus 9 minus 3 is plus 6, means 589.9 nanometer. So our answer matches option B, 589.9 meter. Next question again is on Michelson interferometer. So here we have Michelson interferometer where we are adjusting to give a fringe pattern of concentric circles with source of light whose wavelength is 500 nanometer. How far must the movable arm be displaced so that we get 100 fringes emerge, means the number of fringes that come out are 100. From the center, wavelength is this, so how much the arm should be moved so that we get 100 fringes shifted? Again the same formula, 2, this is the distance divided by lambda, so we need to find out this delta D. So delta D will be lambda delta M by 2. Lambda is 500 nanometer, 10 to the power minus 9. Delta M is 1000. This is 2. This will be 250 times 10 to the power minus 9 plus 3, which will be 250 times 10 to the power minus 6 meters. The answers are in centimeter, so 250 multiplied by 10 to the power minus 6, 1 meter is 100 centimeter. That means 10 to the power 2. Minus 6 plus 2 is minus 4. 10 to the power minus 4 centimeters. So, okay. When I'll put it in decimal, this means 1, 2, 3, 4. 0.025 centimeter is the correct answer. So option A is the correct answer. Okay, we have last question, question number 11. It is on Michelson interferometer as well. Here we are using Michelson interferometer with red light of wavelength 632.8 nanometer, and it existed for a path difference of 20 micrometer. Okay, we have to determine the angular radius of the first ring observed. Angular radius of the first ring observed. Okay, so we know at the center we get dark spot, or we consider that at the center we are getting dark spot, then the maximum number of order for central dark spot will be given by the maximum we can get if the D is fixed. Okay, if D is fixed to 20 micrometer, then the maximum order we can get is 2 times 20 micrometer, 10 to the power minus 6 meters, divided by 632.8 times 10 to the power minus 9, which will give us divided by 632.8, which was 0.0632. 10 to the power minus 9, when it will go in numerator, it will become 9. 9 minus 6 is 10 to the power 3. So it will be 63 more fringes will be same. Okay, or 63 order we can, sorry, this is 63 order. With this particular d value and lambda value, we can see maximum 63rd order. So if we know, let's consider the center one is dark, that means this is the maximum we can see 63rd, and after that this will be 62, and the next will be 61, like this. Okay, so what we need to find out here is angular radius of first ring. Observe. Now we know path difference for finding out the dark fringe is given by this relation. From this, cos theta, where theta comes from the angular inclination, this will be m lambda divided by 2d. Now m we want to find out is for first ring. We have been asked determine the angular radius of first ring. Maximum we can see with this particular d and lambda, maximum order we can see 63, means the center thing is 63. First ring, this is not ring, the first ring is this disc kind of thing. That means first ring is 62nd order. Lambda is given to be 632.8 nanometer, 2 times, and d is 20 micrometer. 20 times 10 to the power minus 6. When we'll evaluate all this, we'll get 62 multiplied by 632.8 divided by 2 divided by 20. This will be 90.84 multiplied by 10 to the power minus 9 and multiplied by 10 to the power 6. This will be 980.84. 6 minus 9 is 10 to the power minus 3. That means 0.981. Okay, this is cos theta. That means theta will be cos inverse of 0.981. And we'll find out this, cos inverse of 0.981 will get 11.1867. We are getting 11.1868 degrees. Okay, and our answer is matching with these 11.2 degree. When we will take it up to first decimal digit, then it will be 11.2 degrees. So option A is the correct answer. So these were the questions based on this week's experimental and theories that were given in this week's lecture. And so we discussed Newton's ring experiment, its theory and experiment, Michelson interferometer, and we did questions based on this. I think next week we will be discussing in detail the theory behind diffraction and various things related to it. So okay, let's finish. I'll end the session now.